Hi everyone, please welcome. My name is Armando Soares. I'm computer science professor from Federal University of Brazil. This is my presentation about an automated approach to identify source code files affected by architectural technical debt. Let's go. So, there is the main context that's to be analyzed before start the presentation of this paper. For example, imagine that the architectural technical debt is the technical debt more difficult to be identified because the complexity of large-scale systems. The problem statement about this study is because about 36% of effort to maintain a software system is weighed with technical debt, where the highlight technical debt is architectural technical debt, according to Basker, Martini, and Bosch. As we can see, the most challenging aspect to identification in software process and complex systems is to identify architectural technical debt. Imagine if you can identify the main files impacted by architectural technical debt, we can use a process to measure and monitor the impact throughout the software development life cycle. What is the main goal of this paper? The main goal is to create an automated approach to identify ATD and its impact on source code files. The justification of this study is to create a better way to extract critical source code artifacts from Git repositories, because it can help and support and gain insights about architectural technical debt to facilitate the identification, measurement, and monitoring. So, about the research questions. What are the research questions guides this study? The first one, how to identify code artifacts affected by architectural technical debt, the most important fact. The second two, how effective and useful is the proposed solution? About the research design, we conducted a literature review about ATD to discover patterns and understand the main concepts, techniques, and methods to identify ATD. We also conducted a case study about TD in Ericsson to understand how to manage technical debt. Then we used design science process to propose our methods. We discuss with more details in the next slides. The proposed method. So, it was based in the following DSM phases. The phase 1, the problem identification. The phase 2, identify objective and solution. The phase 3, hypothesis definition. And finally, demonstration and evaluation of the method. We discuss the details in the next slide related to design science methods, more specific to case study in Ericsson. The base proposition and hypothesis used in this study. The presence of ATD are files that have the following characteristics. The first one, the files that impact on software architecture. The second two, constant change together. The third, the files that generate recurrent effort. And the fourth, propagate changes in other files. We use these propositions to create the proposed method. About the summary of the proposed method, you can see in this picture the general view of this proposed method. In the phase 1, we get the historical data. In the phase 2, we select architectural smells and the important metrics like frequent occurrence of of commits, accumulated log of commits, and the Maccabi complex metric. The phase 3, we select architecture smells, for example, cycle dependence and hub-like dependence. The phase 4, we select critical source code files. And the last phase, we report the critical files with all hypothesis characters. In this picture, you can see more details about the proposed methods. So, this method is available online in the following replication kits. In general, you have URL of repository, and after you execute and perform the methods results in the files with cycle dependence, hub-like dependence, and selected files can indicate architectural issues as a list of files. During the proposed method, we developed a support tool to collect data and calculate metrics from Git repository. This tool is called sysHappAnalysis, and this sysHappAnalysis is available online. Also, we created two set of scripts to execute and perform the methods. The set of scripts is available online too. So, this is the design science method with more details. So the problem identification is related to challenges faced by developers and architects from Ericsson to handle and manage architectural technical debt. The solution design, basically, we design a solution to address the challenges faced by developers and software architects from Ericsson. The goal of the solution is to create an automated method to use as a practical way. After we created the proposed method, we evaluation executing the proposed method in Apache Cassandra repository. We select the range of commits from 3.0.0 to 3.11.11 to be analyzed because this version is the production version in Ericsson. Finally, we conduct a semi-structured interview with Ericsson developers who maintain the Apache Cassandra. Next, this is some details about the proposed methods using DSN. In the phase 1, we extract the data from the repository, more specifically the Git repository Apache Cassandra. In the phase 2, we select architecture smells and calculate metrics using specific thresholds. In the phase 3, we calculate quartiles and select critical files using the third quartile to select imlock and fock. In the phase 4, we identify critical files with code change using cyclomatic complexity more than 50 and generate dependence matrix among all files and select files with code change with dependent critical files. Finally, in the last phase, we reporting indicating source code files with ATD. As we can see in this graphic, we select only the 12 classes that satisfy the hypothesis and defined in the methods. Related to RQ1, how to identify code affected by ATD. As we can see in this table, we have 12 critical files that has a lot of lock over time and increase cyclomatic complexity over time, and we have a lot of classes impacted by these 12 critical classes. As we can see in this slide, we can check developers' feedback from the interviews. Um, for example, you can see that the developers interviewed agreement with the range of commits. Also, they agreement with the 12 critical files selected. And finally, related to this RQ1, all the developers interviewed agreement with 251 files impacted by critical files. Related to RQ1, how effectively and useful the proposed solution to identify the code artifacts that indicate the presence of ATD. Basically, the files that can be impacted by ATD was showed to the developers, and the percentage of the changes using line of code in the change commit analyzers. As we can see in this table, about 78% of files has recurrent efforts to be maintained. Finally, we ask about change propagation of critical classes, and the developers agreement has agreement with the percentage of the propagation, and we show the number of line of code changes in the set of files, and the developers agreement with this number, showing that there is important to refactor or to maintain these files, because these files can be more effort to be maintainable over time. Finally, the sum up of this paper was based on the study conducted and evaluated with Ericsson partner in a real-world industrial setting, and we can be observed that the proposed method is feasible for identify architectural technical debt without the need for a software architecture specialist. Also, several promised avenues for future research directions include expanding ATD code analyzer. Maybe we use impact analysis of ATD on software quality metrics. Also, we use augmented ATD identification using machine learning methods and techniques. We use these methods to prioritization and refactoring of ATD items. And finally, we can integrate the ATD management into software development process. So, thank you very much. If you have any questions, you can do now, or you can send a message to my email. Thanks again.